I worked really hard this week and now I can take some time off. Have some fun. Something to look forward to. There is a freeing feeling when you're up in the air. Going upside down, hanging there for a second, weightless. You have a known set of maneuvers, a sequence, and you just keep flying them over and over until you figure it out.
Our planet and our civilizations are changing faster than ever before. Join me as I travel the globe talking to startup founders using technologies to make our world more interesting, accessible, and livable. These are the entrepreneurs that are creating the future we will live in. This is Now Go Build. There are few inventions that have changed the course of human history as drastically and quickly as powered flight. When the Wright brothers succeeded at the first extended powered piloted heavier-than-air flight, they started a chain reaction of epic proportions. From a short flight powered by a small four-cylinder engine at Kitty Hawk in 1903, it was only 44 years before Chuck Yeager broke the sound barrier. And only 14 years beyond that, before Yuri Gagarin was carried into the first piloted orbital spaceflight. In less than a century, advancements to aviation have changed the face of business, medicine, politics, war, and even our cultural awareness. It is hard to imagine a world without flight. And while this hasn't deterred the impulse to innovate, introducing change into an established social and economic system with a momentum of its own can be difficult. The aviation industry is responsible for 12% of the CO2 emissions from all transportation sources today. Airplanes and helicopters are also noisy and require large dedicated areas of land for operation. And now, more than ever, modern air travel is poised for a substantial climate-friendly leap forward. I've traveled to Burlington, Vermont, to meet Kyle Clark, the CEO of Beta Technologies. The search for effective electric flight is nothing new, but it seems that Kyle and his team may have found a solution. Kyle, it's spectacular what we have here, but there must be some history behind this because it's your personal journey. So tell me, how do you get into building airplanes?
Well, it starts with just loving aviation and have an insatiable desire to consume technology. My father had a machine shop. He was working at the university at a machine shop, and I was working there in the summer. So I got access to knee mills, lathes, welding machines, plasma cutters, and I saw the amazing things that the machinists there were creating, and seeing that other people are making amazing machinery and devices, and then applying that to your dream.
Is the aerodynamics and the fluid dynamics of electric airplanes different from let's say, fossil fuel airplanes?
What you can do with electric is certainly different. You don't have to carry all the detriments around the inefficiencies of fossil fuel burning and cooling when you design an electric aircraft. The distribution of electric propulsion is way easier than the distribution of fuel-created propulsion. And that allows you to have vertical takeoff and landing because you can use constant torque electric motors to stabilize the aircraft in different phases of flights. I think we can build a commercial aircraft that does meaningful organ tissue delivery missions over ranges that make sense.
Okay, so you have to tell us a bit about that because there's a particular use case that you had in mind.
Martine Rothblatt was the founder of Sirius XM Radio.
Okay.
And then she went on to found United Therapeutics because her daughter was diagnosed with pulmonary hypertension. So she decided she was going to find a cure for her daughter. Well, it turns out the cure that she found fixed a lot of people's organ challenges, but it requires twice as many transportation elements. You have to explant it, you got to bring it to a repairs facility, then you bring it back out into the organ network. They're doing that with helicopters, ambulances, and jets right now, which it's polluting, it's expensive, they're unreliable. Well, what if we were to do it with a point-to-point aircraft that was all electric? And that was the initial catalyst of the vision to create a vertical takeoff and landing aircraft for a real cargo medical application. You can see, I mean, it's a big airplane, right?
Yeah.
It's got a 50-foot wingspan, it's 44 feet tip to tail, and it's 14 feet high. Total takeoff weight is 7,000 pounds. And one of the core features that you notice here is the motor's way in the back, right? And that's so that we can exploit the benefits of electric propulsion, which is it's very, very thermally efficient. So we don't need a lot of cooling. We don't need aspiration to breathe and burn fuel.
Yeah.
You know, typical airplanes, they have a wing and a motor out in the front. By putting the motor in the back, you get a much more aerodynamic shape because the swirl of the propeller doesn't go over the fuselage, and it actually accelerates the boundary layer of fluids and puts it behind the aircraft, leaving a low wake, which is low wasted energy. A little bit of air comes in this port right here, right? It goes down into here, and it goes around a motor that's actually in this region right here. The inverters are back here, and then that little bit of air comes out this slot, right? And it turns this propeller, and what's neat about this, there's no gearbox, there's no anything, it's just spinning right on bearings and pushing that motor around.
Developing engineering simulations in a collaborative way was time-consuming and cost-prohibitive before the power of cloud computing. The team at Beta had figured out how to use a host of tools to accelerate engineering models, collaborations, and iterations.
So kind of the heart of the system is the electric propulsion system. So here, if we turn the corner in here, we build the electric motors, and we have two big forms. One of them is the electric motors that pick the aircraft up in the air, and the other is the electric motor that pushes it forward. The pieces that get hot, the wires, the semiconductors, the controllers, everything that can fail is put in there redundantly. So in our motors, for example, there's two completely independent motor windings. And we wind that up in a way that it's very, very controlled. And there's pole pairs that match the magnetic pole pairs around the rotor of the motor. And then the inverter, of course, in 3 phases, actuates the current such that the current goes this way when the magnetic field goes this way, so you have a force going this way. So then you're constantly pulling that motor and creating torque, and that's it. You just put the current through the wire, through the magnetic field. There's no pistons, there's no aspiration, there's no spark plugs. It's an incredibly simple system.
I'm a mechanical engineer by training. My background was actually turbo machinery. And then I saw the light. I said, hey, these electric machines have much, much higher efficiency. The mission that we're on at Beta of electrifying flight is super, super interesting. Not only from, developing cool new gadgetry, but it's a step change in efficiency. Best turbo machinery out there, like the holy grail for turbo machinery, is be above 30% efficiency. We're talking 95% efficiency with these machines. The whole goal for these motors is to be as powerful as possible and as light as possible. And so every ounce that we're going to save on this design is going to help us fly a little bit further on the same battery energy.
These longitudinal booms that go down the length of the aircraft. And you'll see there's 4 rotors on the top. And those 4 rotors each have redundant motors inside them. And those stabilize the aircraft in hover and during transition. But as soon as you get going, you turn them all off. And that super efficient wing, 50 foot of laminar flow wing, then provides all the lift that you need while those rotors are stowed. The vertical tail is offset to the side, so the wake actually misses the tail. So the tail has good authority. Another neat feature, you'll see the boom is actually bent just a little bit. It looks like it's sagging. It's because the entrained flow goes up and over the wing and comes down. And that saggingness matches the natural flow over the top of the wing, and therefore those are more aerodynamic. We use all kinds of really rapid prototyping techniques to go from the digital models to the physical systems, whether it's laser cutting or 3D printing or rapid machining. All those things are really, really important. For elements of the airplane that are not required for structural integrity, for example, we 3D print that. Well, this is a pilot armrest where we'll put the load cases in and the boundary conditions of that armrest, and then we'll ask the computer to design a part that's optimized without any manufacturing constraints for shape, given the material properties. So then they'll use this to approximate the geometry that they can manufacture. And that's that iterative, digitally driven process of optimization. This is one battery right here. It's 600 pounds. And you can see they're gonna pick the battery up with a little electrohydraulic lift. There's 5 batteries all in the belly. When there's an odd number of batteries that are centered around the center of gravity of the plane, you get to take the center one out and maintain the same balance, right? Or you get to take number 2 and number 4 out and keep the same balance.
Hi.
How are you doing?
I'm good. How are you?
Thank you. I mean, you're building quite innovative batteries, so I assume you get lots of data back as well that drives the design of it.
There's a lot of data that gets generated from the design. There's a lot of communication that goes in there, so you can see, what's going on almost at the cell level, like the voltages and the temperatures, because you want to make sure that if something happens to one of these individual cells, it's not going to take the whole pack with it.
In an airplane, if you fail a battery cell, you want everything to perk up and get a little stiffer and stronger all of a sudden and make it less likely to fail because you're coming in for a landing, for example.
Yeah.
We want things to fail on.
To be honest, in data centers we have a similar problem. I mean, if your transformer outside gets hit by lightning and you have to switch over to your diesel, that in general used to cause all the servers to go off. So we designed new switches to be able to switch so fast that you could keep your servers on.
You keep bumpless transfer.
Yeah.
So this is one of the many places where we aggregate massive amounts of data. So starting with the build of the product, in this case the motors, we track that particular part all the way onto the airplane, so it has a complete digital history of how it's behaved the entire way.
This is your test environment. Basically, you build your software and your systems for here, but then you have to move them onto real aircraft. So how do you can make sure that there's a consistency going from this to a smaller aircraft and to your ALIA eventually?
Yeah, that's exactly right. So when we release new code, it goes through code check, simulation environment, small scale aircraft, Iron Bird, all before it goes and flies on the big aircraft. So all the headers, the data, and the data rates have to be parsed by the same tools. So here in the Iron Bird, we get all the same data points we get on the real aircraft in the same format, so that the engineer can use the tool to analyze it here as they do in flight test. You physically can't do that across 300 engineers here, doing it on people's laptops. You've got to put it on the cloud. There's A, too much data, B, you need it accessible, and it's not only accessible to the engineers here, but you have partners that are in other parts of the world.
It's a collaboration.
It's a collaboration.
We talked earlier upstairs about failure, which is crucial. And so I always think about the experiment, you measure, and you learn. So how do you ensure that your learnings over time, I would say, are recorded for the next set of engineers that you bring on board?
We have to aggregate that data and make it accessible to all the engineers. So that's important that we have common data storage methods, and then everybody has access to it. And then we provide people the tools to parse that data. You get a much higher effective data transfer between engineers and technicians and pilots and other people. Incredible transparency around failures, and then everybody gets better.
All right, running through for a left-hand pattern, taking off to the northwest. We clear?
Prototyping is the key to collecting reliable data with repeatable form factors and environments. And with remote control scale models, a human isn't put at risk when testing new flight systems. I find myself thinking that this team may have the coolest job at Beta. So it's not as much testing flying, it's much more the sensoring and the navigation and things like that.
After we proved that it could do what we're doing right now, that it could actually fly as intended, then it became about taking all of the flight control code and sensors and putting them in this and flying it before we fly it on the big plane.
Yeah, okay. So what are we seeing here?
it's actually the same interface you'd see with the full-scale vehicle. So these 1/5 scale, all of the vehicles in this fleet essentially run all the same hardware, they run the same code, they run the same sensors as the full-scale vehicles. So we are using all the same exact tools. You can see things like airspeed, angle of attack, ground speed, battery voltage, how much current we're using instantaneously, and dealing with the challenges of those with a high magnetic interference environment, and essentially figure out if we have any warnings or flags or if we're experiencing bias in our measurements.
Collecting this data is just the first step. Applying it to every aspect of development and production while still collecting new data from every subsequent scale, simulation and full-sized aircraft is a monumental computing task, one that is prime for AWS.
So there's about 960 data points coming down during flight test at a rate of 100 times a second. Because we use computational fluid dynamics and systems modelings, we have a complete plant model of the aircraft, we get to take all that data and go refly it in a simulated environment and make those models better and better and better. So that at the first level, the sensory systems and the data systems allow us to develop aircraft much, much faster.
So this is one of many simulators that we use to help design the aircraft and then train the pilots how to fly. All the data systems are consistent in the simulator to the real aircraft.
Okay.
This is Alex. He's responsible for doing a whole bunch of programming of linking the simulated environment to real environments.
So we've used Sims at Beta for both for the development and for tests of the aircraft. In the future, we'll be using it for the production of the aircraft. You're looking at our engineering development simulator. Here we have the same flight controls as you'd find in the actual airplane.
And now we're going to start moving forward, and you'll see our speed start to build up here, right?
Okay.
And now as we transition onto the wing, we're going to slowly lower our lift lever. Now we hit about 85 knots, and we're going to turn off this top deck. And you see our rotors stop up here, and we're just going to park them. So as we get close to the ground, we get into ground effect, and we start pushing the air against the ground, and it creates a little bit of a pillow on the ground. Oop. Oh, no, you're okay. Just tiny motions, like this, like okay. This. Yep. Okay, now if we want to land, we move it that far down. And as we come in to buffer the ground, we move it that far up. And we get into ground effect, and we set it down. Beautiful.
If we can use what we have now for technologies at a faster rate and get them adopted, then we're going to turn the corner on climate change faster. By having better estimators based on the data, we get to use more of the battery, which means we have a more viable commercial product. An aircraft like this and a distributed mesh network that's data-driven exploits all of this great infrastructure that we have at unused airports, because you can go shorter and shorter takeoff or even go off airport to do these things. We can now go point to point. And that allows us to go from a distribution center to a fulfillment center directly without going to an airport, which is way more sustainable and efficient because you travel a much shorter distance.
What did you need to do in terms of infrastructure to also make sure that this whole system can work?
The connection with reality tells you that you can't just build the airplane and expect it to solve the problem. The problems that our customers have need the entire ecosystem of things to make it happen. They need the airplane, they need a charging system, and that charging system has to work in harmony with the aircraft. That charging time becomes critical to the mission success, closure, and the economic viability of the aircraft. So we took it upon ourselves to develop the charging technology, and then the placement of those chargers affect the success of the launch of the product. And that charging network becomes incredibly valuable because it's an enabling step to launch our product, but it also gives our customers a platform in which to operate.
So you guys have been partially funded out of the Climate Pledge Fund. How important it is to get these kind of, let's say, investors on board to help you sort of reach your goals?
We wouldn't accept an investor that was not aligned with the mission, the mindset, and the passions of the business. It's the same thing true with our board members and the people that work here. When you share a common goal, it makes it easy to work really hard for each other.
To work really hard for each other. That's the bottom line, isn't it? To see a need, come together and share our time, money and expertise to find a solution. We could very well be at the dawn of electrification of aviation, and the potential for cloud applications in this field appear to be limitless. Imagine the benefits to medical systems, humanitarian aid programs and public transportation. Not to mention the very important impact it would have on CO2 levels and climate change. The magic of flight is undeniable. To defy gravity and soar above the clouds is a dream widely shared. Kyle and the team at Beta can certainly be added to the list of the great pioneers of aviation. At the very least, they're showing us that we've only just begun to dream about the possibilities of flight evolution and where it can take us.